Hello, welcome back to a second day of the 2020 Pacific Causal Inference Conference. I'm the chair of the first session. In this session, we have three speakers. First one is from Emilija Perkovic. From University of Washington. Emilija is a system professor at the University of Washington, and her research interest in causal inference and graphic model. So today she will share with us about total causal effect in MPDAG, identification and minimum enumerations. Emilija, are you ready?
Yes, I'm ready. I just can't turn on my video. Can I? Okay, great. So do you want me to start my video or no?
Yes, please. You can start.
Okay, great. Now I can. Wonderful. All right. Wonderful. Thank you so much. Thanks for the invitation and for organizing the conference. So yes, as Andrew said, today I will be giving a talk on total causal effects in MPDAGs, identification and minimal enumeration. This is joint work with Richard Guo, who is now a postdoc in Cambridge. All right, so the goal of this talk is essentially to, talk about two of our results and kind of, I guess, convince you that MPDAGs are models that are interesting, graphical models that are interesting to use. Okay. So first, I'm going to go through some background that probably a lot of the attendants already know. But just to set up the question, the goal for us will be to estimate a total causal effect of some treatment A, variable A, on some response Y. And we all know that the gold standard for doing something like this for estimating causal effects is to run a randomized control study where you intervene and set A to a particular level, and you randomize A to, for example, two different levels in two groups. And after a certain time, you compare the effects of the response in these two different groups to get your estimate of the total causal effect. So I will think about the total causal effect and some change in Y that happens as a result of some intervention that sets A to a particular level. And I'll label these interventions using Pearl's do notation. Now, the challenging thing for us is that we're trying to estimate these total causal effects using observational data rather than randomized control studies data, or perhaps observational data and some additional expert knowledge. And this is challenging to do because essentially the interventional distribution of the response is not necessarily the same as the observational distribution of the response when you're just conditioned on the same level of the treatment. Okay. So throughout, I'll be using this DAG. So throughout the first part, I'm going to be using this DAG as an example. So this is a causal directed acyclic graph, or a DAG for short. Each vertex in the graph represents a random variable, and each edge here represents a particular causal effect. So if we're interested, for example, in estimating the total causal effect of A on Y, and we have the ability to conduct a randomized control study, we can essentially control the level that A takes. And in the randomized control study, that is, we can represent the graph in that study by kind of cutting off the inputs into A. Because now we're randomizing A to a certain level, we have full control of it. This D and B no longer has any input into A. And so in this setting, once you intervene and set A to a particular level, now any change that happens in A, so if you change A to a different level, that can only propagate to the response through these causal paths, so through these kind of directed paths from A to Y. And so that's why in these randomized control studies, we can just compare different responses and get an estimate of the total causal effect. All right, so a little bit more background. So how do we connect DAGs and probability distributions? So I'll say that a DAG is causal if all observational and interventional distributions or densities factorize according to this DAG. So this is an observational distribution, factorizes as each vertex or variable given its parents in the DAG, and the interventional distribution factorizes exactly the same way as the observational one, except that you drop the term that would be random in A, because now A is fixed. All right, and so another thing to note is, what is a total causal effect? So there's many ways to define it. The definition that I will be using is, I will just say that this total causal effect will be some function of the interventional distribution of the response. So some definitions that people use, in particular when estimating a total causal effect, is, let's say, a difference in expectation when you increase the treatment by 1 in these interventional regimes. For example, if you have a linear system, you might also define it as this derivative with respect to treatment of the expectation of the response. It can be an odds ratio, a risk ratio, or some other quantity depending on your setting. But it's always some function of the interventional distribution of the response. So I will just try to identify the interventional distribution of the response. And I will say then that this total causal effect is identifiable from observational data if this interventional distribution can be computed or expressed in a particular way from the observational joint distribution. And so now, if you remember the previous slides, we know that if we know what the causal DAG is, then by this definition, every total causal effect is identifiable. So this interventional distribution of the response is just the marginal of this joint interventional distribution, and we've seen on the previous slide how to factorize that in terms of these observational quantities. So this way of identifying the causal effect is, I will refer to as the generalized G formula. It has other names, but this is just what we refer to it in our paper. Okay, so that seems to solve our problem. So if we know the causal DAG, every total causal effect is identifiable. So now I'm coming to the question of interest for me here, is that this causal DAG is generally not something that we can learn from observational data. And so what can we why can we assume it? What can we do instead? So in fact, even if you observe all the variables in the causal system, if you assume that, and you have an infinite amount of data without making kind of parametric assumptions about your model, what you can hope to learn from observational data is a structure rather like this. So this is a different type of graph, which is known as a completed partially directed acyclic graph. So you will see that it has, so I just made certain edges gray. So these are the directed edges. They are directed in the same way as in the DAG. But now in this graph, we also have some undirected edges. So for example, this one between A and F. And what that means is essentially that we don't know if in the true causal DAG, the edge points from A to F or from F to A. So we kind of leave it undirected. So you can think about this graph as a summary model that represents many different DAGs in an equivalence class, and we don't know which one is the truth. So the question could be, for example, when can we identify a causal effect given a structure like this that we could hope to learn maybe from observational data? Or perhaps another thing that we could do is, if we are willing to make certain parametric assumption, or we have information from prior experiments or experts, we might have additional information on top of this thing that we can glean from observational data. So for example, perhaps we know from experts that D and B cause A and that A causes F. We can include that into our graph. Sorry. And we can then propagate this knowledge to learn some more information perhaps. And what this gives us is now yet a new graph called a maximally oriented partially directed acyclic graph, which still has some undirected edges, but much fewer than the one we started with. So you can again think about this as a summary graph, but just represents a narrower, a more refined class of graphs compared to the one we started with. Okay, so the question for me is in this first work is, how can we identify, or can we identify causal effect given a structure like this, and how? So this is the big picture idea that I have in mind when I think about these two projects, is I think about having some observational data and perhaps some background knowledge. Now throughout in this talk, I will assume no latent variables. That's something that we will hopefully build out to in future work. But given these two pieces of information, I can learn the causal structure with background knowledge, say using a causal discovery algorithm, or if you have some other way. And that gives us a causal graph, which can be one of these three classes of graphs. So DAG, as we've seen, CPDAG, or an MPDAG. And really, an MPDAG is the most general of these three classes, and it subsumes the other two. So you can think about a DAG as like an MPDAG, where you've added background knowledge that was fully informative and no other directed edges remain, and a CPDAG where the background knowledge you've added was not informative at all. So that's why this talk is called also identifying total causal effects in MPDAGs. So this class will subsume the other two. Okay, so how can we actually identify a total causal effect given something like this? So the work that I'll be talking about today starts kind of assuming knowing you have access to some of these causal graphs, and then moves to this area from there. All right. So there are several ways or approaches you can use to identify a causal effect. Here I've listed two, one of which we've seen before. So this generalized G formula, or the truncated factorization formula, lets you identify, so express this interventional distribution in this type of form, right? So this integral or sum, depending on your interest, of a product of certain conditional distributions. And another kind of popular way of identifying causal effect is using adjustment. You might have also heard this referred to as controlling for confounders, or the backdoor criterion in certain cases. But adjustment implies many different forms of these graphical criteria. And essentially what adjustment means here for me is just that you can express this interventional distribution in this particular form, so that there is a certain set Z that we will call an adjustment set that lets you express this distribution in this form. So if there is an adjustment set, it lets you identify the total causal effect or this distribution with this functional, and otherwise in the DAG you can also identify it with this functional, and there's usually other ways also to identify. Or if there is one way of identifying a causal effect, there's usually more than one. But I will focus on these two approaches. So for the adjustment, there's been quite a lot of work on it, and actually we have a graphical criterion that lets you know when you can use this formula exactly. And these graphical criterion can be applied in a DAG, a CPDAG, or an MPDAG. And there are certain other graphical classes that it can work also in. However, for the G formula, or this truncated factorization formula, we know only how to apply it in the DAG. But there is one advantage that you have using the G formula compared to this adjustment formula, and that is indicated here in these arrows, meaning that there are causal effects that cannot be identified in this form that could be identified in this form. So the fact that we don't have a way of using this formula in the CPDAGs and MPDAGs means that we lose identifiability for certain causal effects. So the goal of this work was to generalize this G formula to these CPDAGs and MPDAGs. And so to do that, first, know that if we have a summary graph, so if we don't have a DAG, the identification of a causal effect is not always possible. So, so first we wanted to figure out when is a causal effect even identifiable. And so now I will move from this MPDAG to this one. So I'll just assume that instead of being interested in an effect of A on Y, I'm interested in an effect of A1 and A2 on Y. Okay. So in this case, actually, we have this MPDAG, and so you might try to identify this causal effect with adjustment. And so what you will notice is that for this A2 and Y, F is a common cause. So F is a compounder for A2 and Y, so you'd like to adjust for it. That would need to be in an adjustment set. But at the same time, F is also on this causal path from A1 to Y, which lets you know, if you've done some work on adjustment, that this is not something you should adjust for, because adjustment wants to adjust for confounders but leave the causal paths open. So adjusting for F and using just that adjustment formula will lead you to a biased result. Okay, so this is an example, right? We have this path that is confounding, but at the same time this F is on a causal path, so it's a problem. So this is exactly one example where adjustment will say this effect is not identifiable, but the effect, in fact, the effect is actually identifiable. Okay, so we've creatively named this the causal identification formula, and I'll try and present it now. So first, as I've explained, in these graphs, you cannot always identify a causal effect. So first, we have a necessary condition for when that is possible. So for a causal effect to be identifiable at all, we would need to have that all proper possibly causal paths from A to Y start with a directed edge in our graph. And so, for example, if this edge between A1 and F was undirected, then this A1FY would be a proper possibly causal path that starts with an undirected edge. And in that case, we would not satisfy this criterion. And so why is that a problem? So that's a problem because if this edge is undirected, some intuition, then we don't know whether this path is causal or non-causal, right? So if it was non-causal, we could have adjusted for F, but because it's causal, we cannot. So essentially, not knowing this orientation kind of confuses you about what to do with F. All right, so that's the necessary condition. And we can see, by the way, that in our graph, this condition is satisfied because all the neighborhood of A1 and A2 is directed, so there is no way that there is a proper possibly causal path that starts with an undirected edge. Okay, so once the necessary condition is satisfied, the formula looks like something like this, and it has this very scary theorem that I will try to explain. So just the first thing, at first glance, you can notice that it looks very similar to the generalized G formula because it's a generalization of this. And so it's an integral or a sum over products of certain conditional densities. But the difference is in what is here behind this integral. So this includes all nodes or variables that have a causal path to y that is not through A. And it's also different in what is in each of these segments. So this SI contains all the nodes. So this SI is a partition of these nodes into an undirected connected set in G. And why we will see on the next slide. So just an example of how to use this in our case. This would be the formula that you would obtain if you would use if you would use our method. And how do we obtain it? So first, you can check whether the necessary condition is satisfied. In this case, it is. Then you want to get all the nodes that are ancestors of y but not through A. So to do that, you might first remove A because that makes it easier to see what is an ancestor of y. So in this case, it ends up being that all of the nodes are ancestors of y. And next, what we want to do is we want to just partition this group of nodes into just undirected connected components. So to do that, it's easiest to see it if you just remove all the directed edges, and then we can see that we have three connected components here, F, Y, and then BDC. After that, to write out the formula, the only thing you need to do is put everything back together. And then the formula takes this form. So it's Y given its parents in the graph, F given its parents in the graph, and BCD given its parents. So BCD here has no parents, so it just remains like this. So in that sense, it's very similar to what happens in the generalized G formula. Okay, so that's the first part, and I'll quickly go through another piece of work. Which is what do you do if this causal effect is not identifiable, right? So we've now kind of covered the case when it is identifiable. So now we were wondering what happens if it's not identifiable. So let's consider this kind of MPDAG for an example. So again, we want the effect of A on Y. Now we have this path ACY that starts with an undirected edge. And this is something called a possibly causal path, meaning there is a DAG in which this is a causal path. And so we're wondering how, in this case, if we cannot identify the effect, can we at least kind of enumerate possible causal effects? So something that you might remember from the beginning of the talk was that if you know what the causal DAG is, then you can identify any effect, and you can then use some estimator to estimate it. And so one thing that you may think to do is just enumerate over the entire set of DAGs represented by this MPDAG and estimate the effect in each, assuming that that's the true DAG. And so can we kind of come up with an idea like that? So what we want, right, we want some partition of this equivalence class such that the effect is identifiable under each group within a partition. And again, we are not the first to work on this. So the approach that I described, given kind of enumerating brute force over all DAGs, was used in Matthaus et al. In 2009. It was called the global IDA. But in that same paper, they also noticed that this is kind of overkill computationally to do, and also that there is a better way if you want a quick algorithm. They've noticed that as soon as you know the neighborhood of A, the orientation of the neighborhood of A, that already gives you a way to estimate or identify a causal effect. So for example, they enumerate then over the valid parent set of A, and they call this the local IDA. There have been some other follow-up works on this as well. Recently, actually, Liu et al. Also noticed that actually that's also too much. You don't need to kind of enumerate over the entire neighborhood of A. It's enough to know the orientation of those edges that are next to A that are on possibly causal paths to Y. And so they've done this approach. And once we've come up with this criterion, what we've seen is that, okay, as soon as I know the proper possibly causal paths so that they start with a directed edge, then we will have the identification of the total causal effect. So we thought we could use that, because one thing that all of these approaches have in common additionally is that none of them are minimal, meaning that they will all kind of give you a set of possible effects that is larger than the true actual set of possible effects, which might not be an issue if you have infinite data. But supposing you have a true graph and finite data, and if you're using different estimators to estimate this effect that is in fact the same, you might get slightly different answers, meaning you can get a set of different estimates that are different simply because of your sample size and not because of any true causal difference in the data. So we wanted to kind of eliminate this ambiguity, right? So if you were to output different effects, we want that to imply that there's some difference, some causal difference. Okay, so what we've done is we've looked at this criterion and we said, okay, so if we just enumerate over all the graphs that have different orientations on these edges that are on proper possibly causal paths, that should be enough, right? So our first try here is to just pick an edge that is next to A that is on a proper possibly causal path, and then add this background knowledge. So create two graphs that each have different background knowledge. So one that has a background knowledge that it's directed in one direction and the other one with the opposite knowledge, right? And then kind of propagate that until you have that this condition is satisfied in all the graphs. And so that list gives you a list of MPDAGs, essentially a list of effects. So let's do that in our example. So I've just removed one edge that doesn't have any impact on this graph. So suppose we start with orienting. So in this graph, we have two paths, so ACY and ABCY, that are both proper possibly causal paths that start with an undirected edge. So we can try and orient AB first. So we add AB as background knowledge in one direction, AB as background knowledge in the other direction. And so in both of these graphs, what you can notice is we still have an undirected edge here, AC. And in both cases, this is still a proper possibly causal path. So in both cases, we still need to add the orientation of AC in both directions. So we do another level of recursion, and that gives us these four graphs. And so we thought, okay, that must be then minimal. There are only four effects here. However, it turns out that these two graphs in the middle actually represent the same causal effect, which means that we've added kind of too much background knowledge. In fact, both of these can be represented by this one. So you can see it removes this information on A, B, and BC. And in this graph, the causal effect is already identified. And why is that? So we have A, B, C, Y still starts with an undirected edge. However, this path is no longer possibly causal, because if you were to make it a causal path, if you were to make it A to B and B to C, you would have a cycle. And our assumption here is that we have an underlying directed acyclic graph. Okay, so actually, you can see that if instead of starting with AB first, you start with AC first, and you add the background knowledge of AC, and then in this case, you need to still add the background knowledge of AB, but here we know you don't. You end up with three graphs, and that is the true minimal number of different represented total causal effects. So in fact, our final algorithm is just a small modification of the first one, which says instead of just picking an arbitrary edge, you pick the one that is on a shortest proper possibly causal path. And that gives you the result that you get a complete and minimal output of a set of possible total causal effects. Right, so that was kind of my talk. You can find all the algorithms I've talked about here on GitHub. I think this may also be on CRAN now. Yeah, that's it. If you have any questions, I'll be very happy to answer. Yeah.
Thank you, Emilija. Any questions from audience? We have a few minutes.
No problem.
So actually, I have a question.
Yep.
So how do you apply this in the real data set? How do you check those assumptions, whether assumption hold? Can you give a quick answer on the application of the approach to a real data set?
So which assumptions are you talking about?
Like
Just...
the graph, the relationship is known. The causal graph is known.
Yeah, so I am, yes, so you're right. What I'm doing is I'm assuming that I have a particular graph, and I'm assuming that's the true causal graph. Now,
So
the one thing that, sorry, I'm just going to find one. There we go. So I am assuming this is a graph that we've learned from observational data or was given to us in some other way, and we're assuming that this is correct. Now, of course, if this is not a correct graph, the answers that we get are likely wrong. But if it is the correct one, then we're getting correct answers. So we don't really, so in this work, we don't do a check of whether this is actually the correct graph. And so that is definitely something that that is kind of an open problem, is how do you know whether your graph is correct? But what I will say is that as opposed to starting from a DAG, we start from something slightly more general, meaning that I guess one benefit of using this approach over just starting from a DAG is that it lets you kind of misspecify the orientations of these edges, for example. So no matter what orientations I have here, this should still give you a true answer because this answer should hold for all of those graphs. But it's not robust to misspecification. For example, if you've forgotten to include an edge, or if one of these edges here that is very important is oriented wrongly, then of course we get wrong results. And I don't really know how to deal with this, to be honest. So that's still
interesting. Yeah. Could you go back to the graph you just showed?
Sure. This one?
Yeah. So this one, you need to have a two arrow, two directions in this graph.
Yeah.
So I'm wondering, do you have to require in your graph, you need to have some directions?
Yeah, so in order to enumerate over possible effects, you don't. You can, it will just take longer. It will be a larger set of effects. So in this graph, for example, the way that we've obtained this for the example, this is not a representation of anything necessarily, is that we've assumed in this case just that A is a cause of Y. So if you assume that A is a cause of Y, you can add this direction, and that further orients this edge. So if that is something, for example, that you can assume in your in your research, then you can try and add certain informations based on that. But yes, if you want to work with completely undirected graphs, that is possible given this enumeration method. You will just end up with a very large set. So as much information as you can give it to kind of narrow it down, that's helpful. But another thing that this method assumes is that we have no latent variables, which I think is probably the strongest of all of the assumptions. And so that is something we're hoping to eliminate at some point in the future, meaning to apply it for cases where you can allow latent variables.
So if you don't have any edges, that translate into have a wider convenable. So how does that translate into the statistical?
Yeah. So for example, here, if I didn't know that A was a cause of Y, right. I would have all of these graphs of all of these effects that we've, let's say, estimated in this case. But you would also have in your range also all the effects where, in the case where Y is a cause of A. But for example, so in that case, so if Y is a cause of A, then the effect in our assumption would be 0 because we're assuming that there is no cycle, right? So if Y is a cause of A, then A cannot also be a cause of Y. So in that case, all of those effects would be 0. So essentially, by assuming that A is a cause of Y, what we're doing here is we're bounding away the effect, bounding it away from 0, just not sure how much. But this was just for an example. In certain cases, if you have observational data, you might be able to conclude something like this just from the data itself. But in some cases, right, if you don't want to assume anything, then there is no way. Then then in your list of estimates of possible causal effects, you will always have effects that are larger than 0 and also effects that are smaller than 0, meaning that 0 will be contained in your interval. So you will not be able to conclude much in that case, I think.
Okay, thanks. Thank you.
Yeah, no problem.